Hi, this is Dr. Viv. Let's now discuss operating on vectors. So I have here a vector that changes with time. In other words, the x, y, and z components separately change with time. And the vector as a whole also is regarded as changing with time. Now, of course, you can differentiate such a vector and you can differentiate it multiple times. So that's one thing you can do. You can also integrate this vector. So let's focus on differentiating the vector in this video. Integration works the same way. Let's start with an example of something like this. So I have here a coordinate system. Let that be the z-axis, that's the x-axis, and that's the y-axis. And we are looking at some particle moving around. Let's say we are trying to track the movement of a housefly. Okay, so here's the housefly, and it's buzzing around in a very complicated way. And one way to describe the motion of the housefly is to consider the vector known as r of t, or the position vector, that tracks the movement of the housefly at any given moment of time. So as this housefly moves around, this vector also will keep changing its magnitude and direction. So we can define various quantities associated with r of t, the position vector. So let's first write down what r of t might look like. It's going to have, using the ijk unit vectors, x times I hat, y of t times j hat, plus z of t times k hat. And once you have this position vector written down, you can then define various other vectors that arise from it. The velocity vector is got by differentiating. So you, from this in this direction, you would differentiate. If you want, you're given the velocity vector and you want to get the position vector, then in this direction, so I'll write d by dt here. And if you want to go in this direction from velocity to position, you would integrate with respect to time. And that's going to be dx by dt plus dy by dt j hat plus dz by dt k hat. So in this manner, you can get the velocity vector, and once you have the velocity vector, you can go further and find the acceleration. So if I write velocity as dr by dt, which is what I've done there, then the acceleration would be dv by dt, and you can further differentiate acceleration if you want. These are known as jerks. So the jerk of the first order would be dA by dt, etc. So you can do this pretty straightforwardly. So what I would like to do now is to look at some properties of this operation. All the usual calculus properties hold, except they hold in the vector setting. So let me look at some basic properties. The first thing you'll do is, if you multiply by this vector by a scalar, suppose I take lambda and multiply it, and lambda could be a function of time, okay? And I multiply it by the vector a, and I take the derivative. Now we're going to use Newton's notation. Newton liked to save paper. So Newton's notation was, this is called Leibniz's notation, d by dt. But Newton's notation is to indicate time derivative as a dot. So you write v equals r dot, and you will write a equals r double dot. Very compact. So if you want to differentiate this, lambda times a dot is just going to be by the Leibniz rule, lambda dot times a plus lambda times a dot. And lambda is also supposed to just change with time, so this is not generally 0. If it's 0, then that means lambda is a constant. And then you can do all other rules the same way. For example, if let me just do the dot product and the cross product, and the remaining rules you can just do on your own. If I have A dot B, now don't make the classic mistake of expanding out A dot B, because then you'll get a very complicated expression involving theta and so on. But the best way to do this is to apply Leibniz rule similar to that. So this is going to be A dot B plus A dot B dot. Get into the habit of not changing the order of the terms themselves. You can certainly keep the order the same. And the cross product, A cross B, and that habit will pay off when you come to the cross product, because you don't want to mess with the order of A and B, since the cross product is Q commutative. So this is going to be A dot cross B plus A cross B dot. As an example, let's try to find the velocity and acceleration vectors in polar coordinates. This is a good exercise for us to do to figure out how to think about vector derivatives. So in polar coordinates, in two-dimensional polar coordinates, to keep things manageable for this video, I'll take to be x and y, and then the general point can be described also by coordinates called r and theta. So let's take this point P here. The position vector r of t fully describes how far it is from the origin, and then the angle vector theta of t fully describes exactly where it's located counterclockwise from the positive x-axis. Now, the only problem with this coordinate system is that the unit vectors travel with the particle. So if I have the unit vector in polar coordinates er and e theta, you'll notice that er is radial to any circle you can draw, and e theta is tangential to that circle, and er and e theta of course make a 90-degree angle. If you take this to the third dimension, say for example with a cylindrical coordinate system, you'll also have a ez coming out of the page. So one thing we have to do is to actually describe the unit vectors er and e theta in terms of the unit vectors I hat and j hat. So let me draw a mini coordinate system here itself to do that. That will also be your angle theta, as will this. And your I hat is going to be along your x hat, and j hat is going to be along y hat. So let's try to write expressions for er and e theta as a function of theta and possibly r. So er, if you look at it, it's got x component of cosine theta and a y component of sine theta. So this is going to be cosine theta as a function of time, I hat, plus sine theta as a function of time, j hat. And e theta, well, the cosine theta component now becomes in the y direction, and the negative sine theta component is in the x direction because it's pointing backwards. So I'm going to get negative sine theta I hat plus cosine theta j hat. So now I have both the unit vectors written out, and they're both functions of time. So now we can proceed with our differentiation of each of these. So when I have er dot, using Newton's notation, cosine theta derivative is negative sine theta, and I'll not write the theta as a function of time to save space. And then once I do that, I also have to go and differentiate with respect to theta using the chain rule. So that's theta dot I hat plus cosine theta, theta dot j hat. What about here? E theta dot. Now when I differentiate sine theta, I'm going to get cosine theta. So that's minus cosine theta times theta dot I hat. And here I'll get negative sine theta because the derivative of cosine is minus sine times j hat. Well, if you think about it, looking at this expression and that expression, they look the same except that it's multiplied by theta dot. So I have here er dot equals theta dot times e theta. So that's a pretty important side result we get right away. The rate of change of the r unit vector actually happens in the theta direction. Now let's do the same thing for this. What interpretation can you give this? Well, e theta is just the minus of er, except with the theta dot again. So we have e theta dot equals minus theta dot times er. So the geometric interpretation of that is that the derivative or the rate of change of the tangential vector is in the radial direction. So it looks like their directions, and that makes kind of sense. If you think about the circle, if you're moving along the circle, the e theta vector is going to shift. Let me draw this e theta at a different location just to show you why this makes sense. If I have a location, let's say here. Now, by the way, this point is simply not rotating, but that's one possible motion. So the new ER vector will be there and the new E theta vector will be there. If you think about it, the rate of change of the E theta vector is, as it's gone from here to there, so it's in this direction. It's in the R direction. And the rate of change of the R vector, it's gone from being from here to there, is actually in the theta direction. So the rate of changes are in the complementary directions. It will be in this tangential direction for the R vector, and it will be in the radial direction for the theta vector. That's the origin of this mathematical statement. Now, once you have this, you can find out anything you want. For example, the position vector r of t can be written as r of t without any vector sign times er as a function of time. Now, if I want to find the velocity vector, all I would have to do is take dr by dt. And so that's going to be this r dot times er plus r times er dot. And for er dot, I'll just substitute from there. So I get r dot er plus r theta dot e theta. So this is sometimes called the radial velocity. It tells you how much of this is caused by things moving directly outward. And this is called the angular velocity. Well, the theta dot is called the angular velocity, and r times theta dot is the radial velocity due to the angular velocity. So, or the tangential velocity, I should call it. So it tracks both components, the part that's directly heading out and the part that's changing like that. Now, what about the acceleration? Let's go ahead and do that. The acceleration is got by taking another derivative of this thing. You're going to get more terms now. So if I do this, I'll get two terms right away. So that's going to be r double dot er plus r dot er dot. That's what I get from the first term. And the second term is going to give me 3 terms because each of these can be differentiated. So I'll get r dot e theta differentiating r first, and then differentiating theta dot first, I'll get this. And lastly, I'll differentiate just e theta, and I get that. The last step is to substitute for e theta dot and er dot from those expressions. So let's do that. I'll get r double dot minus er dot is theta dot e theta, so that gives me r dot theta dot e theta. And then here I have, there's no minus sign, it's a plus sign. Here I have plus another r dot theta dot e theta. And then here I have r theta double dot e theta. And here I can write this as minus theta dot times er instead of e theta dot. And so that gives me r times theta dot squared e theta. Now I can club together the r terms and the theta terms. Let me do that in the last step. R double dot minus, wait, there are way too many unwritten terms here. That's r here. So r double dot minus r theta dot squared er, and then notice that this is 1 plus 1, so that's 2 r dot theta dot plus this term here r theta double dot e theta. This is an especially interesting expression because it gives us some interesting insights on what happens in the coordinate system that is rotating. And if you are in a car that's turning a very sharp curve, you'll experience some of these things. This is the usual radial acceleration. Nothing to be said about that. It tracks how fast the particle is moving out, the rate of change of that. This is the usual centripetal acceleration that you, or if you take the minus sign into account, it's a centrifugal acceleration, the degree to which you get flung out when you make a turn. This is an interesting term, and this is called the Coriolis acceleration. The Coriolis acceleration comes because you have a coordinate system that's rotating. Coriolis was a French engineer, and he first noted that when you fire a cannon, the cannon ball doesn't go in a parabolic arc, but the parabolic arc shifts with respect to the Earth because of Earth's rotation. That's what this Coriolis term gives us. And that's the usual tangential acceleration, similar to the tangential velocity there.